Hello, we are back with negative refractive index. Today, we are going to see why the refractive index will be negative, both the mathematics and the physics part. So let us start with the mathematics part. So to know why a refractive index n is negative, when we are using a double negative material, which means mu is negative and epsilon is negative, or permeability is negative and permittivity is negative. Now, mu is negative means we can write mu as minus 1 into absolute of mu. Similarly, for epsilon negative, we can write it as a minus 1 into absolute of epsilon. Now, root over of epsilon mu, when both are negative, that we can write as root over of negative epsilon into root over of negative mu. So, root over of negative epsilon is root over of minus 1 into root over of absolute epsilon. Root over of minus 1 is I, so that we can write as I into root over of absolute epsilon. Similarly, for minus mu, we can write I into root over of absolute mu. I into I is root over of minus 1. So I into I is minus 1. So this product will give us minus 1 into root over of absolute epsilon into absolute mu, which is minus root over of epsilon into mu absolute. And root over of epsilon into mu is n. Therefore, n, or refractive index, is negative. This is one way of saying why n is negative using simple mathematics. Another way of saying the same thing using simple mathematics is write n as root over of epsilon mu. Both are negative, so it is root over of minus epsilon into minus mu root over of that. Now minus epsilon we can write as exponential I pi into absolute of epsilon, because epsilon I pi, exponential I pi is minus 1. Similarly, for mu we can write exponential I pi into absolute mu. So that is equal to root over of exponential 2 I pi into absolute epsilon into absolute mu whole root over. Now root over of epsilon 2 I pi is epsilon I pi. So we can write it as epsilon I pi into root over of absolute epsilon into absolute mu. Now, exponential I pi is minus 1. So this is equal to minus of root over of absolute epsilon into mu. So this is a second way of proving that n is negative or refractive index is negative. These two are mathematical proof or analytical proof, simple explanation of n being negative. Now let us look at physics-based explanation. So using physics equations, we'll try to prove that n is negative or refractive index is negative. So let us consider that a physical explanation. For that, what we will do is to find out the sign of the index. Index means refractive index of a left-handed material or DNG material. We will use Maxwell's equation, because the wave equation is leading to ambiguity that we have seen. Wave equation does not change. Whether it is right-handed material or left-handed material, wave equation is fixed. So it does not change. And therefore it is leading to ambiguity. So since it leads to ambiguity, we will not consider the wave equation, we will consider the basic Maxwell's equation. So mathematically, it is impossible to resolve whether the index is negative or positive if we consider the wave equation. So we will not consider the wave equation. We will start with basic Maxwell's equation. Now we are considering a LHM, left-handed material, or DNG material. If we are considering a DNG material, then epsilon is equal to minus epsilon 0. In free space, we are considering it. So epsilon is equal to minus epsilon 0. Mu is equal to minus mu 0. So permittivity and permeability both are negative. And now we will use these two in Maxwell's equation. So when we are going to use these two in Maxwell's equation, we will consider uniform plane wave in free space. And if we consider uniform plane wave in free space, then Maxwell's equations are of the form, the two curl equations we have seen, they are of the form k cross E. K is the wave vector cross electric field is equal to minus mu 0 omega h. Similarly, k cross h is equal to epsilon 0 omega mu. So this is for uniform plane wave in free space. Now we are going to use the usual definition. What is the usual definition? For usual definition, we will define KLHM or KDNG. K is the wave vector. KLHM means the wave vector inside the LHM medium or the DNG medium. So wave vector in the LHM medium or DNG medium is equal to NLHM into K. NLHM is the index in the medium. So KLHM, let us define this as is equal to NLHM into K. K is the wave vector in free space, normal free space. So KLHM we find out in this method. So KLHM is equal to this, where NLHM is the index. Now if we rearrange this equation, from this we will get K is equal to KLHM by NLHM. So K we are going to get as KLHM by NLHM. Use this second equation in the first equation for K. So if we use the second equation in the first equation for K, so the first equation will be K LHM by N LHM cross E is equal to mu 0 omega H, from which we will get K LHM cross E is equal to minus mu 0 into N LHM into omega into H. Similarly, we will get K LHM cross H is equal to epsilon 0 N LHM omega into E. Now remember this third equation. Let us start with this third equation. So this is the third equation that we have got. K LHM cross E is equal to minus mu 0 N LHM omega H. K LHM cross H is equal to epsilon 0 N LHM omega epsilon. From this we have to find out what is N LHM. Now on this same thing, we are going to deduce using this equation, the following equation. KLHM cross E is equal to minus of minus mu 0 omega H. How? Because K cross E is equal to minus mu 0 omega H, or K cross E is equal to mu minus mu omega H. Now for the DNG material or LHM material, mu is equal to minus mu 0 that we have seen or we have taken. So put for mu minus mu 0, and for the DNG material K is equal to KLHM. So using that we get KLHM cross E which is in the DNG material. So that will be equal to minus of minus mu 0 omega H. So inside the DNG material, vector is K, wave vector is KLHM, mu is equal to minus mu 0. We have put that. Similarly, for the H, we will get KLHM cross H is equal to minus epsilon 0 into omega E. So this is the third equation. This is the fourth equation. Now what we will do is identify what is NLHM by comparing third equation with the fourth equation. Left hand side are same in both equation 3 and equation 4. Left hand side is same. On the right hand side, in the third equation, the first one of the third equation on the right hand side, we have got minus mu 0 omega h. In fourth equation also we have got minus mu 0 omega h. What is additional in equation 3 is NLHM. Therefore, if you compare these two, NLHM is equal to minus 1. Similarly, compare 3 with 4, you will get NLHM is equal to minus 1. So, by comparing equation 3 and equation 4, we get NLHM is equal to minus 1. What is NLHM? NLHM is the index, refractive index in the DNG medium, double negative medium. And that is minus 1, which is negative. So from physics, using Maxwell's equation, we have proved that the refractive index is minus 1 or is negative. Now let us consider another physical consideration. Like two mathematical considerations we have taken, we will consider two physical considerations. So the second physical consideration. We know from Snell's law, sine theta is the incident angle divided by sine theta t is the transmitted angle. Their ratio is equal to minus k2 absolute by k1 absolute. K2 is the wave vector in medium 2, k1 is the wave vector in medium 1. So this is minus k2 by k1, and since it is minus k2 by k1, this is negative, therefore n2 by n1 is negative. If n2 by n1 is negative, then n we define as n2 by n1, refractive index of second medium, to the refractive index of first medium, that is n. So from that we get n is negative. N2 by n1 is negative, so from that n is negative. So n is negative, so n is equal to minus, we know by definition n is equal to c root epsilon mu, the root epsilon mu that is negative, so n is equal to minus c root over of epsilon mu. So it is negative. So from both physical considerations, we have seen that refractive index in a DNG material or in a LHM material is negative. So that we have proved. Now, what is the consequence of this, of it being negative? Let us consider one consequence, which is the Snell's law. Now, in this Snell's law, we will consider two mediums, medium 1 and medium 2. Medium 1 is a right-handed medium, which means here refractive index is positive. Medium 2 is a left-handed medium, which means here the refractive index is negative. Now we are incidenting the wave from the right hand medium or the medium 1 towards medium 2. What happens at the interface? Remember that when we measure angle, if we are measuring the angle in a clockwise direction, it is negative. If we are measuring the angle in anti-clockwise direction, it is positive. Now we'll see whether this angle is negative or not. This theta t transmitted angle is negative or not. And now the NRH means refractive medium in the refractive index in the right-handed medium. That into sine theta I is equal to NLH, refractive index in the left-handed medium, into sine theta t. This is the Snell's law. Now NLH is negative, which means that we can write as minus absolute of NLH into sine theta t. Now, from this equation, we can find out what is theta t. So, theta t is equal to minus of sine inverse of NRH by absolute NLH into sine theta I. Now, the right hand side is negative. Since right hand side is negative, theta t is negative. Theta t is negative means the angle is measured in the clockwise direction. So the refracted angle or the transmitted angle will be in the clockwise direction. As you can see in the figure, the refracted angle is in the clockwise direction. So instead of being anti-clockwise direction, it is in the clockwise direction. So incident angle and the transmitted angle, if you look at that, then the incident wave and the transmitted wave, they are appearing as if they are being reflected from the normal. Normal is considered as a plane. If you take normal to be a plane, then the incident wave is getting reflected from the normal. It appears as if it is getting reflected from the plane. So with that, we will stop for today. And tomorrow we will see, or next time we will see some more consequences of negative refractive index. Thank you.